All right, we're gonna go over the problems on the practice test. Help us prepare for the test. Here we go. So the first one is just ask us to state the absolute maximum and the absolute minimum. Now, absolute means it's the highest point, right, on a graph. Now, a graph may or may not have a highest point. It might go up forever, for example, but some of them do, right? And so for this one, we see that both of the arrows are going down, so there has to be a highest point. And it looks like the highest point would be right here, right? Right here. Okay, so that would be the point 5, 3. That would be the location of the absolute max, right? And the actual max is 3, but point is 5, 3. Okay, now absolute minimum, you might want to set this as the absolute minimum, but if you notice, this graph has arrows that go down forever. So that's actually not the smallest value. This one will have none. Because if it goes down forever, that means it doesn't have a lowest point. Okay, now relative max and relative min is any time it goes from increasing to decreasing. So what I like to do is just draw the arrows. Right, this looks like it's going up, it's going up, it's going down, it's going up, right? It's going down, it's going down, it's going up, it's going up, it's going up, it's going up, it's going down. Okay, so anytime it goes from increasing to decreasing, that would be a maximum. So that looks like right here, right? That would be a relative max, right? Because after that point, it starts changing from positive to negative, from increasing to decreasing. Think of it like the highest point in the area, right? So this would be like -6, 4, or actually -6, 2. Sorry. All right, and it looks like this is the potential highest point in the area right here, right? Because it goes from up to down. That looks like -1, 0. And then this one right here looks like the highest point in the area. It goes from increasing to decreasing. That would be 5, 3. And that would be all your relative maxes, highest point in the area. And then you can kind of see the lowest point in the area would be these kind of guys. This one and this one. That's a min because it changes from decreasing to increasing, exactly the opposite of the other one. So that would be the point -3, -6. And then the second point would be 3, -4. Now, if they're asking you for intervals of decreasing, we have 2 intervals of decreasing. It looks like this is one of the intervals because the arrow is going down, right? We have another interval here. So we actually have more than 2 because we have another interval here. Okay, so remember, intervals are x values. So my first interval looks like it starts here, -6, and it stops decreasing here. So the first interval of decrease is -6 to -3. Remember, we use parentheses for -6 and -3 because it's changing from increasing to decreasing, which means at that point, it's actually neither decreasing or decreasing. Okay, and then remember that it stops decreasing after that. Like if we look at the blue part, there's this portion right here where it's not decreasing. So it stops decreasing for a little bit, and then it picks up again. It looks like right about right here, right? So right here is where it starts decreasing again, and it looks like it stops decreasing right about here, right? So that would be the interval -1 to 3. Right? And then my last interval, it looks like it starts decreasing here, and then never stops decreasing because the arrow says it goes down for forever. So that would be starts again at 5 to infinity. That would be my intervals of increase, right? Sorry, decrease. Now, increasing is just labeling all of these points where the arrows are going up, right? So it looks like it starts off from the left forever because it's going down forever. So this would be negative infinity. So that just means from the left all the way to this point right here, which looks like -6. It's decreasing. Oh gosh, I did. Yeah. So I just did, these were all decreasing. So go ahead and put, right? So instead of putting them in the right place, I put increase. Now we're doing increase, right? So my fault. These are decreasing. Hopefully that doesn't confuse you. Okay, so now we're doing increasing because the arrows are going up, right? So negative infinity to -6, it's increasing, and then they're going up from here to here, which looks like -3 to -1. So it stops going up for a little bit, and then -3 to -1. And then it looks like it stops going up again because you have a little blue, and then went from 3 to 5. It's increasing. Sorry. So this is increase. Sorry about that. All right. Another mistake here. These answers won't work. Okay. So what I want you to do is like do your best to come up with an equation that would model. Now, the key thing here is recognizing that we have 3 roots, right? And we're going to assume that those are multiplicity of 1 because I'm going to give you equations on the test to choose from, right? But remember, all of these cross the axis. So they have to be either multiplicity 1, 3, or 5. So let's just assume that they're all 1. So my first root, the second thing we know is it also has to be like some odd function, like a cubic, right? Because the end behavior is up on the right and down on the left, right? So if we just write the roots, right, like this, if the root is -4, the factor is +4. If the root is -2, the factor is +2. And if the root is 4, the factor is -4. You always change the sign to find the root. So that would be a potential equation that would model this solution. Now, we don't know if that's correct, but that's the best we can do, right? We don't know it's correct because this could potentially be like 3, right? Because we don't know what the power is. We just know it's an odd power, right? Or, for example, this could be 5, any odd powers, right? But our best guess is 1. Okay. All right. So we're using multiplicity here to try to do a sketch of the graph, right? So the first thing I need to know is the power. Like, and this is like the power, like if I were to multiply the polynomials out. I don't want to actually do that, but I know that this one, if I multiplied it out, the highest power would be x cubed, which is 3. And for this one, if I FOIL it out, the highest power would be 2. So our highest power is 5th. So we're gonna think about x to the 5th, right? We know that x to the 5th has this behavior where it's positive on the left, right, and negative going down on the left and going up on the right, right? And we know that because all polynomials have the same end behavior as x cubed if they're odd, and the same end behavior as x squared if they're even, right? So since the power is 5, which is odd, that's how we know the end behavior. Okay, now the roots is, let's set both of these parts equal to 0. Right, so when I take the cube root, it's just 0. And when I subtract, I get -1. But we know polynomials have 3 solutions. So really, this is -1 3 times. It's a repeat solution, right? And so we know one of our roots is going to be right here. And we know, since it's an odd root, that it's going to cross at the root. Right? So the graph is going to cross the x-axis right there. It's not going to bounce. Now, the second one is x minus 2 squared. And we can use the same logic as the last one to say that this would be x equals positive 2 twice. Right? Which is right here. But we know that since it occurs more than once, an even amount, right? So 2, 4, 6, this one occurs twice. We know it's not going to cross at the axis. It's going to bounce. So our best guess of a graph would be something like this. This is an odd root, so it crosses. This is an even root, so it bounces. Something like that. Okay. All right. The end behavior, right? Now I can make this look as messy as I want. For end behavior, all we need to do is look at the highest power, right? So I'm looking at that the highest power of x is negative 3x to the fifth. And I know that 5 is odd, right? It's an odd multiple, right? It's an odd number, which means I'm thinking about the graph x cubed, because all polynomials that are odd power have the same end behavior as x cubed. And x cubed looks like this, right? But this one is negative x cubed, which would be a reflection. So it kind of going to look like this. Just flipped it, right? Now, if I put a little axis here, remember end behavior as it goes this way and as it goes this way, what is y doing? Is it going up or down, right? So for the left part, right, we always start from the left, so we're doing this way. So if we say from the left would be as x approaches negative infinity, right? So as it moves to the left, as it gets smaller, we notice that the arrows point up, which means that as we move to the left, y gets bigger. So if x gets smaller, y gets bigger. Okay, now let's go to the right. So let's focus in on the right part. And we notice the arrow is down on the right, which means as we move in the x direction to the right, those are bigger values of x. Y actually gets smaller. Okay, so those are our end behaviors. We use infinity and negative infinity to say bigger, smaller. All right, we're going to perform some operations on rational equations. So our first step is we have subtraction here. So we need a least common denominator. So let's do some factoring here. All right, so I can use the x method on the bottom. I have 3 on top, negative 4 on bottom. I'm looking for two numbers that multiply to 3 and add to negative 4. They have to both be negative if they multiply to a positive and add to a negative. And my answers are 3 and 1, because negative 3 times negative 1 is positive 3. Negative 3 plus negative 1 is negative 4. So this would factor as x minus 1, x minus 3. And then this one is x minus 1. Now here you're going to see that these ones have a factor in common. Namely, they both have x minus 1. Right? So whenever they have a factor in common, the least common denominator is going to be the one with more stuff, right? The biggest one. So this would be my least common denominator. My least common denominator is the bottom here, right? So in order to make this one equal to that, I have to multiply the top and the bottom by my least common denominator. Okay. Once we do that, we can write it as a single fraction. So I'm going to write 5, and then I'm going to do some distributing here since I'm multiplying top and bottom, right? 2x times x is 2x squared. And 2x times negative 3 is positive 6. Don't forget that we're multiplying by negative 2x, right? Okay, so let's do some rearranging and adding like terms, see what we can do. Okay, so we have a 5 and a 6, right? Those will cancel out, they'll combine. to get 11. And now the bottom is this. Okay, now I know I'm done when there's nothing else I can do, and I know that 11 is a prime number, so I can't take out any common factors. I can't factor this anymore, so I'm done. Okay, here we have multiplication and division. So this looks crazy. What we're going to do before we multiply and divide is we're going to factor, and then we're going to immediately flip, right? Whenever we divide, remember this one flips. So this bottom goes to top, and this top goes to bottom. Okay, so the first thing I see is, I don't like the fact that this is negative x minus 1, right? We want to cancel, like, we want to make it positive x minus 1. So let's just change that by taking out a negative 1, and that'll change that to x plus 1, right? I'm hoping something is going to cancel. I'm hoping the top has an x plus 1. Right, now the top, we can use the x method to factor. So I'm looking for numbers that multiply to 30 and combine to negative 11. It's a positive number, so they have to be the same sign, and it's a negative, so they both have to be negative. And we know that 6 and 5 goes into 30, and 6 plus 5 is 11. So this top one factors as x minus 6, x minus 5. Right? And I see that x minus 5, and I have the same kind of worry here. It's like, I would rather the x be on the left if I could avoid it, right? So let's do some manipulation. Same trick as before. Let's take out a negative 1 and change this to x minus 5. Remember, when I take out a negative 1, it just changes the signs. Okay, now I'm going to write this as times, and the bottom looks like a difference of squares, right? So in other words, we have, right, we have 1 squared minus x squared. And we know that that factors as, whenever I have two things being squared, it's the numbers being squared added and the numbers being squared subtracted. So that's what I'm going to put on the top. I'm going to flip, so the bottom goes to the top, and the top factors as a difference of squares. Okay, and then the bottom, which is the top right here, so now we're going to factor this part right here, right? So let's take the x method. I got 6 and negative 7, so it has to be negative 6 and negative 1, right? So this would be x minus 6, x minus 1. And that's because negative 6 times negative 1 is positive 6, negative 6 plus negative 1 is negative 7, right? So now I'm going to try to cancel everything out that I possibly can. So I have a bottom, x plus 1, that's the same thing as 1 plus x, right? I have an x minus 5 and an x minus 5. I have an x minus 6 and an x minus 6. And these two look very similar to each other, right? So let's use that same trick, right? Let's use the same trick on the top. So right now what we have is we have 4 times 1 minus x over, we have a negative here and a negative here, so that's positive 1, and then we just have an x minus 1 on bottom, right? But I can change either the top or the bottom by taking out a negative. So let's just do it from the top. Let's take out a negative 1, so let's make it negative 4, and then that's going to switch the signs of both. And now I can cancel out, and that messy thing was just a fancy way of saying negative 4. All right, so here we're going to be solving. So when we're solving, remember, we're going to multiply by what's called the least common multiple. Okay, so in this case, we're not going to factor the tops. We're just going to factor the bottoms. Okay, so let's use the x method right here. I got negative 10 and negative 3. Two numbers that multiply to a negative have to be the opposite signs. And we know that 5 and 2 work. And it has to be actually positive 2 and negative 5, and that's because negative 5 times 2 is negative 10, and negative 5 plus 2 is negative 3. So it's x plus 2, x minus 5. Now let's look at these two. Once again, we're kind of like multiplying by the least common multiple, also called the least common denominator. So it looks like the least common multiple of x plus 2 and x minus 5. This one's the biggest number, so let's multiply every term when we're solving, we multiply every term by the least common multiple. And that's going to get rid of all the fractions. So I multiply that one by that. I multiply 1 by this. And I multiply this one by this. And I'm going to cancel out anything that I can. Okay, so the first one, nothing cancels. So when I multiply this by 1, I'm just going to get x plus 2 times x minus 5. When I move to the second one, it looks like an x minus 5 cancels. And then I just get 1 times x plus 2, which is x plus 2. When I move to the 7, it looks like everything cancels, and I just get 7. Okay, so I should FOIL here. So everybody gets a turn because I'm multiplying binomial by binomial. Okay, x times x is x squared. X times negative 5 is negative 5x. 2 times x is 2x. 2 times negative 5 is negative 10. Plus x plus 2 equals 7. Let's add my like terms. I got a negative 5x and a 2x. That gives me negative 3x. I also have an x right here, so that actually gives me negative 2x because I have another like term. Right? I have a negative 10 and a 2. And I'm going to go ahead and move that 7 to the left, right? Because that's, maybe I'll just take another step. So that's negative 8 equals 7. And then I'll subtract because with quadratics with 3 terms, I want everything on one side. So I'll subtract the 7. And now I'm looking for numbers that multiply to negative 15 and add to negative 2. They have to be the opposite sign, so they're really subtracting to negative 2. So I know that 5 and 3 would work. Right? So this is x minus 5, x plus 3. And then to find the roots, you just change the signs. Or you can set them both equal to 0 and solve. That's what we're doing when we change the sign. All right, graphing rational functions. So there's 5 things you need for graphing rational functions. The first thing you need is to find the holes. Okay, so the holes are, we're going to try to factor the top and factor the bottom. The top factors, because they have a 3 in common, it's 2 terms. We can't use the difference of squares because they're not squares, but 6 is 3 times 2, so they both have a common factor of 3. I'm using the GCF method. The bottom is 2 terms, and it looks like a difference of squares, right? I made a mistake here. When I took out the 3, I wrote 6. I took it out the 3s from 6, so I should have written 2. Right? Bottom is a difference of squares because 4 is the same thing as 2 squared. So this is really in the form like this. Whenever we have a 2 squares being subtracted, that factors as 1 plus and 1 minus. Remember, holes are when I factor and something cancels. So this looks like a hole. Remember to change the sign of the hole. So we have a hole at x equals negative 2. Right? Now, from here on out, this is our function. Because we've simplified. This is our function. But we don't just want the location of the x value of the hole. We want the y value too. So after I find where the hole is, by doing the opposite sign of whatever term I cancel out, I'm going to plug it in to figure out the y value that goes with that hole. And that looks like it's at negative 3/4. Okay, so that's my first part. All right, I think I might need more paper here. So here we go. Second part, after holes, it doesn't matter which one you do next. Just remember that this is our function that we're working with now because we've reduced it, right? You don't want to go with the one that we started with. Okay, so let's find our vertical asymptotes. Vertical asymptotes are when the bottom equals 0. So to find these, just set the bottom equal to 0. And when I solve, I get a vertical asymptote at 2. Okay, so far we have a hole. The hole's at negative 2, negative 3/4. There's my hole, and I have my vertical asymptote. Let's find the roots. To find the roots, you set the top equal to 0, but the top is just 3. And 3 can never be 0, so there's no roots. Right? Okay, so we have holes, we have vertical asymptotes, we have roots. Let's find our y-intercept. For the y-intercept, I set x equal to 0. So in other words, I'm finding f of 0. Right? And remember, f of 0 just means go to the function, which is here. And every time you see an x, replace the x with 0. And we get a vertical asymptote at 3/2, which is 1.5, if you prefer. The last thing we need is the horizontal asymptote. And by this, we compare the degree on top to the degree on bottom. So we look at the degree on bottom is 1, the degree on top is 0. So the degree on bottom is bigger, right? So it grows much faster. So this will have the same behavior. Think about it like, what if I had something like this? What value would it approach? Well, it would approach 0. So we have a horizontal asymptote at y equals 0. Okay, let's put everything together. I recommend graphing the asymptotes first. So we have a vertical asymptote at x equals 2. Vertical asymptotes we usually do with dashed lines. Okay, we have a horizontal asymptote at y equals 0. Okay, we have a hole at -2 3/4. Okay, so -2 3/4 is like give or take right here. Right, it doesn't have to be perfect, but I'm going to label that so that I know what it is. Okay, and then we have a y-intercept at 1.5. So it crosses the y-axis right about here. Okay, now we can do a graph here. It has no roots, so we can figure out what part of the graph looks like. We know it kind of looks like this. It gets closer to the asymptote, never crosses. But we have a problem here because we don't know, is the graph like this? Or is the graph something like down here? Right? So what we do is we do a test point, right, to figure out, is it positive or negative? So we just pick something to the right of the asymptote. So let's pick the test point 3. That's to the right of the asymptote. In other words, let's find f of 3. And that's going to tell me, is it, if it's positive, then it's up, and if it's negative, then it's down, right? So I go 3 over 3 minus 2, which is 3 over 1, which is 3. Okay, so I know now I have a point, 3, 3. So I know at 3, my graph was here. Okay, this isn't a point, that was just, right? And now I can tell that the graph goes like this. All right. We got to expand. Okay, so to expand, let's first start by writing this top as a power. So to go from radical to power, remember the root goes on bottom and the power goes on top. So that's z to the 4/3, right? And then the bottom is x cubed y, right? Now when I divide, I could write that as 2 different logarithms, right? So I could say that this is whatever's on top subtracted from whatever's on bottom, right? So the log of this, and then notice y is also subtracted because it's being multiplied, but it's on the bottom, so it would look like that. Okay, and then let's just go ahead and put those powers in front. So we get 4/3 log of z minus 3 log of x. Remember, that's a important log property. I can bring powers out in front. Okay, just like I can expand logarithms, I can condense them. So I want to make this into 1 logarithm. So I have a power here. So the first thing I do is let's bring that power back up here, because now we're like going in reverse. And let's bring this power back up here. And let's bring this power back up here. Okay, and then I have plus, right? Okay, so 9 is really 9 to the 1/2 is the square root of 9. So really what I have here is I have log, I have plus, so these are multiplication. So that's the square root of 9 times x cubed, because these 2 logs were plus. And then this one will be on the bottom because it's minus. So it looks like on the bottom I have y squared. And I can simplify square root of 9. This is log 3x cubed over y squared. Okay, so we have a logarithm, and we're going to be solving this for an equation. Now, whenever you have one logarithm, we're going to use the fact that whenever I have a log, I can change it to an exponential, right? It's the base to the right side equals what's on the inside. Okay, so in other words, I can write this as, this is the base, I raise it to this power, and it equals what's on the inside. Okay, so let's FOIL this out. So negative 2x minus 3 squared, that really means this. Right? So let's go ahead and FOIL. Right? Negative 2x times negative 2x is 4x squared. Negative 2x times negative 3 is plus 6x. Negative 3 times negative 2x is plus 6x. And negative 3 times negative 3 is plus 9. And that equals 3x squared minus 18. Okay, so let's go ahead and get everything to one side and combine like terms. So if I subtract this 3x squared from this 3x squared, I would get x squared. If I combine these two, I would get 12x. And if I add 18 to 9, I would get 27. Okay, so now we're going to try to factor, right? I'm looking for numbers that multiply to 27 and add to 12. Okay, so 9 and 3 would work. Right, 9 times 3 is 27. 9 plus 3 is 12. So this would be x plus 9 times x plus 3. That equals 0. And so your final answer would be change the signs. Okay, so for this logarithm, I have subtraction. So I'm going to write it as a single logarithm. I have two logarithms. So instead of two logarithms, let's write it as a single one whenever I subtract. Right? The one being subtracted goes on the bottom. Now I can use that property that we used last time. Whenever I have a log base b of a equals c, I can write that as an exponential if b to the c equals a. So in other words, this would be 2 squared equals 2x minus 7 divided by 4x minus 7. Okay, and instead of 2 squared, let's just write 4. This is a rational function, so let's get rid of the fractions by multiplying everything by the bottom. That's going to cancel this, and I'm going to get so I'm going to get 4 times 4x minus 7. That's going to equal 2x minus 7. Let's distribute to get 16x minus 28 equals 2x minus 7. We got to get the x's on one side, so let's subtract 16. So let's subtract 2x from 16x. 16 minus 2 is 14x. If I just subtract, so I subtracted the 2x. Right? If I add the 28, I would get 14x equals 21, and then I would divide by 14, and I would get 21 over 14, which is the same thing as they both have a 7 in common. So this would be what? 3 over 2. Okay, I'm done. Okay, so we have an extra step for this one. So we have subtraction. So let's go ahead and put those together. So let's write it as 1 log. When I subtract, I can write it together. And then the other log. But recall, whenever I have logs on both sides, I can just cancel out the logs. And now I have a rational function. Or a rational equation, I should say. So let's multiply everything by the bottom. Right? And then we get x minus 1 equals, let's distribute to get 3x plus 6. Get the x's on one side, so I subtract 3x and I add 1. And then I divide by -2. Okay, now you have to be careful here because this looks like a solution, right? But notice if I were to plug in this back into here, I would get a negative number, right? And logs can never be negative, right? So this is actually not a solution. This has no solution. Okay, now I should go and double check my solutions up here and make sure we don't get a negative. Okay, so if I plug in 3/2 into here, I would get 3 minus 7. This would also be a negative. So actually, this has no solution. Because when you plug it in, you get a negative. So it looks like it has a solution, but it doesn't. Because when I plug in, like I said, when I plug in 3/2 here, I would get 3 minus 7, which is negative. So that's another one with no solution. Okay, graphing the logarithm. So this is base 3. So the first thing you know is the parent function is this. Okay, so the 3 points you have to know are going to be 1, 0, 3, 1, and 1/3, -1. Okay, so I'll have this negative right here. That's outside the function, so that's a reflection, right? So vertical reflection because it's outside, so my y's are going to be negative. Okay, and then we have this 6 inside. It's inside, so it's horizontal. So it's going to change the x's. Remember, horizontal, we always do the opposite. So you're going to take your x's and you're going to subtract 6. 3 minus 6 is -3. And 1/3 minus 6. I'm fine with just a decimal. That's fine. So 1/3 minus 6 would be -5.66, comma 1. And then we have this +4, right? So this +4 is going to be outside. So it's going to change the y's, make them 4. -5, 4. Okay, I just realized something stupid. So I'm not going to give myself enough space. So let's go back here. So if you remember, we did the reflection first. So we already changed the y. Now we got to subtract 6 because it's inside. Okay, so 1 minus 6 was -5. 3 minus 6 was -3. And then 1/3 minus 6, I already forgot what it was, -5.6. I'll just round that, right? And then that one had the same y value as 1. Okay, so hopefully I didn't lose you there. We did the second step. And then now we have to do the 4, which is outside the function, so it changes the y's. So I add 4 to my y's. All right. Okay, now our asymptote's always at 0 unless we have a horizontal translation, which we do here. We moved it over 6 to the left. So my horizontal asymptote is at x equals 6. Okay, now my points are -5, 4, which is here. My second point is -3, 3, which is here. And my third point is -5.67 and 1. Okay, so I did something wrong here. I know I did something wrong because that can't be right. So let's see. 1, 0. So I made a negative. I subtracted the 6. Then I added 4. I didn't add 4 to this one. That's why. Right? 1 plus 4 is 5. Who teaches this? Okay, here we go. So that will be, give or take, right here. which actually doesn't look much better. So did I do something? Okay, so this one has to be, oh God, let's plot these points again. How embarrassing. Okay, -5, 4 is right here. -3, 3 is right here. Nope, that's not the right point. It's -3, 3. Gosh. And then I have -5.675. Okay, so, oh my gosh, what a struggle. So I put this at, this is be at 4. Okay, hopefully you guys aren't struggling as much as me. Okay, that was bad. So the other point's right here. Okay, so we know that the graph looks something like okay, now I know this can't be. I'm so sorry. I gotta find my mistake. Okay, so that was 1, 0, 3, 1, 1/3, -1. Made it negative. I subtracted the 6. And I added the 4. Okay, so the graph looks something like this. I had a brain fart here. I was thinking that I couldn't be right because I was thinking that logs are reflected, but I forgot that the logs go down like this. So that's what I was struggling with. Not that you care, but now you know. Okay, so almost done. We got about 4 more. Here we go. 3 more. So now we're going to talk about half-life and exponential growth or compound interest. So the half-life formula is, let's try to be consistent. I think I used A of t equals, it's equal to the initial amount times 1/2 times t over k. Okay, so if I use different variables there than on the notes, I apologize, but it doesn't really matter what letter I use. Okay, so in this case, we have to figure out what are they asking for, and this, we notice it's how long. So that means they're going to give us A of t, which is the amount after we let it sit. They're going to give us, as you call this, A initial, right? And then they're going to give us K, which is the half-life. Okay, so A of t, which is, we took 20 grams and, sorry, we took 20 grams, that's the initial. So we started with 20 grams. And then we waited a bit until we reached 6 grams. Okay, so A of t is how long we're waiting for it to decay. Okay, and we have to wait 10 years, that's the K value. So we just plug in our points. So we got 6 goes here, that's the amount after it starts decaying, equals the initial amount. Instead of 1/2, I'm just going to write 0.5. And then we have t over, sorry, I got this wrong, k over t. Apologize. No, it is t over k. Jeez. Okay, and k was 10 years. It takes 10 years for it to decay by half. So first thing, let's divide by 20 to solve this equation. Okay, 6 over 20 is 0.3. So this is 0.3 equals 0.5 to the t over 10. Whenever I have an exponential, I'm going to take the logs of both sides. And the reason why I do that is so I can bring the power down. So I'm going to bring the power down and take the log of the inside. Then I'm going to divide by the log. And then I'm going to multiply by 10. So when you plug it in the calculator, make sure you do the top first, hit enter, right? And then do the bottom. So when you plug this into your calculator, 10 log 0.3, enter, divided by log 0.5, enter. And I get 17.3. What do they want me to round to? Nearest tenth of a year. So it's 0.36. So it would round to 17.4 if it was the nearest tenth. 17.4 years. All right. So for this one, whenever you see money account, we should look for compounded. It's continuous. So that tells me we're going to be using the continuous formula. Not KT, RT. I'm trying to use the same letters as the reference sheet. If I'm using different letters, I apologize. Okay, so they're asking how long, which means we're not going to have T again. So we're going to have A, we're going to have A inverse, and we're going to have R. A is the future value. So we initially invested 54,000. That's how much we initially invested. And it's asking how long for that money to grow to 106,000 if the interest rate was 4%, which when I divide by 100 is 0.04. Now I plug in my values, 106,200 equals 54,000 times E to the 0.04 T. We got to solve for T. So first thing I got to do is divide both sides by 54,000. So I'm going to go to my calculator and say, what's 106,200 divided by 54,000? And I get 1.9667. Let's round to 4 decimals. Now to get rid of ln, to get rid of e, I have to take the natural log of both sides, because the natural log is just base e. When we do that, the powers cancel. So e and ln cancel. Then I divide by 0.04, and I'm ready to plug this into my calculator. Okay, so I go in my calculator, ln. There's a button on ln in your calculator. You should get 16.90. They want to round to the nearest year, so that would be 17. Last one. All right, we got to solve. And notice we have an exponential here. So the first thing I'm going to do is subtract 480. I want to get the exponential term by itself. Okay, 1080 minus 480, that's 600. Times that. Then I'm going to divide by 420, right? So let's see what 1,000, sorry, not 1,000. See what 600 divided by 420 is. Okay, so when I divide this so that it cancels out on the right, I get 1.4286 equals 1.04 times x plus 1. Now to get rid of the power, I take the logs of both sides. And the whole reason why we do that is so we can take that power out in front. So I'm going to go ahead and do that in one step. You can take an extra step if you like. Then I'm going to divide out the logs. Log is just a number, so I can divide it. It'll cancel here, but whatever I do to one side, I got to do to the other side. And then now I can see everything else cancel, but the x plus 1. So all I have to do is subtract 1. So x would be equal to this nonsense, and then you can go minus 1. Now I go to my calculator, I say log of 1.4286 divided by log of 1.04 minus 1, and you get 8.0946. Doesn't say what to round to, so whatever you round to is kind of up to you. And we're done.